All right, so this video is going to go over pages 29 through 31 in your packet. We're going to talk about Newton's universal law of gravitation. So Newton basically concluded that Earth attracts any mass to it. So that's what's holding you to the Earth is that gravitational force. But he basically stated that any two objects that have mass have some natural attraction force to them. Okay, so that means you and any object near you, okay, has an actual natural gravitational effect on each other. Now, it can be minor. That means you're not going to really feel it. Like, you're not going to feel it if something's being pulled away. But there is a small degree of some attraction to any two masses. Now, there are two things that can affect that. One is the mass, okay? So if the mass goes up, okay, so meaning it gets bigger, okay, that attraction force is going to get bigger as well, okay? So that's why planet Earth, okay, has such a strong pull on you, is because it is a huge mass pulling on us. Okay, now if you were to take like a baseball and a softball and put them near each other, okay, it's not going to be really very much. You're not going to be able to tell that force. Now, if you take one of those and replace it with like a basketball, even though you're not going to be able to really tell, is once you make that mass bigger, okay, it's going to create more of an attraction force. Okay, so if mass goes up, force goes up. That is a direct relationship. Okay, now the thing that can hurt it though is distance. Distance is if distance goes up, force goes down. Okay, just think of two magnets in that case. So if you hold two magnets near each other, you can feel that pull. But when you start pulling them away, you feel that attraction force start to weaken. Okay, so that is an indirect relationship. Okay, so if one goes up, the other one goes down. Now, he didn't know how to calculate this, so Henry Cavendish came along and was able to calculate it, and he came up with this constant right here. You don't need to know it or memorize it. That's just a constant like we would use, like gravity's 9.8. This is your gravitational constant. Okay, so you would use that in this equation, which we're going to give you, which is the attraction force equals that gravitational constant times mass 1 times mass 2 all over your distance squared. Okay, so your mass has to be in kilograms. Distance has to be in meters. Okay, so just make sure you're in those. Okay, you have your gravitational constant and in your forces in newtons. Now it says the force is equal and opposite on both masses. Okay, so that means if you have a big mass like this and then a small mass like this, once you find that attraction force between the two, okay, it's equal both ways. Okay, that doesn't mean that the big object's going to have some big, stronger pull than the smaller object. It's just one uniform attraction force between two masses. Okay, so the force is very small unless one of the objects is very large in mass, such as a planet. Okay, so again, like you have a gravitational attraction to any mass around you, but you're not going to really feel it. Okay, that means if you walk away, that object's not going to start following you because of the pull, and you're not going to feel it tugging, okay, if that thing starts going the other way. Okay, but if you take a very large mass like Earth, okay, that's what you feel like when you're being pulled into your chair. That's that gravitational pull. So, example, find the force. So we're looking for force. Between you, a 70 kilograms. So we're going to say you're 70 kilograms. So there's your mass 1. And your book is 2 kilograms. So there's your mass 2. And my distance is 1.5 meters apart. So we're just going to plug in on this one. So force equals your big G. So that's that whole 6.67 times 10 to the negative 11. Okay, times mass 1, which is 70, times mass 2, which is 2, all over your distance squared, so 1.5 squared. Okay, so one couple things to watch out for is do not forget this negative exponent right here, and do not forget this squared right here. Okay, so I see a lot of times that can be forgotten whenever you're trying to calculate it. So just be careful with those. And then when you're typing in the calculator, be very careful. Try to put everything in parentheses, especially anything in scientific notation. If you try to do it all in one shot without any parentheses, that usually leads to some type of mathematical error. Okay, so just be careful with that. And you should get a value of 4.15 times 10 to the negative 9 newtons. Okay, so negative 9 means that decimal will go to the left 9 times. So that is a very small attraction force. So that means it's very small. That means you're not going to really feel it, but there is an attraction there between you and your book. Okay, now it says find the force between you and Earth. Okay, so we're looking for force again. You have mass 1. Okay, mass of the Earth is 5.97 times 10 to the 24th kilograms. There's your mass 2. And the radius of the Earth is 6.38 times 10 to the 6 meters. So there's your distance. Now, be careful with that. I know radius, everybody thinks distance, all of a sudden they get diameter in their head and they're wanting to double that. is when you think of attraction force, it's the attraction force between the center of two objects. Okay, it's not the attraction force like so here's your planet Earth, and we'll say I'm right here. Okay, it's not the attraction force between me and someone on the other side of the planet. Okay, it's me and the attraction force between me and the center of the Earth. Okay, so you do not need to double that radius. So watch out for that. So we're going to plug in. So force we don't know. So force equals our big G, 6.67 times 10 to the negative 11, times our mass 1, which is 70, times our mass 2. Let me get rid of this out of the way. There we go. And our mass of the Earth, our mass 2 is 5.97 times 10 to the 24th kilograms, all over your distance squared. So 6.38 times 10 to the 6th, and that's squared. Now this one's probably the most difficult as far as putting it in the calculator. Okay, so again, just watch out for mistakes like leaving out parentheses, okay, forgetting to square the bottom. Okay, so you should get a value of 684.79 newtons. And if you're ever unsure, just ask us. We're not grading you on your ability to type it into a calculator. Okay, so if you're ever unsure, just ask. Now it says this force is really your weight. Okay, so that right here is your weight. Weight is mass times gravity. Okay, so force equals mass times gravity. So it says find the weight of a 70 kilogram object. So if we were to use that M times G, mass would be 70, gravity would be 9.8, and you get a value of 686 newtons. So if you notice, that's pretty dang close to what we just solved for there. So that attraction force and your weight is technically the same thing. Now, that does not mean you can just use F equals mg for every given problem. Like I could not use that on the force between you and a book because you're using the force of gravity, 9.8. That's between Earth and you, not the book and you. Okay, so that's why you just can't use F equals mg on any given problem. Okay, so this is purely just for finding out what your weight or your force is by the attraction of Earth on you. Now, moving on to the next page. If the gravitational force between two masses is 100 newtons and you double mass 1, triple mass 2, and double the distance, what's the new force? Okay, so remember we said if mass goes up, okay, that attraction force goes up as well. Okay, so it's just going to do the exact same thing. Now the kicker is distance is squared. Okay, so if distance goes up, we know that force has to go down. Okay, but that squared is there, so you got to watch out for that. So what you're going to do is you're going to do the opposite. So opposite, but you're going to square the opposite. And I'll show you what I mean by that here in just a second. So I have my original force of 100 newtons. If you double mass 1, so what we're going to do is we're going to just do this a step at a time. So mass 1 is going to go up by 2. Okay, and then that means our force has to go up. So if mass goes up, force goes up. And it's going to do the exact same thing. So 100, we're going to take our original 100, multiply it by 2, and we get 200 newtons. Okay, so there's step 1. So that part's done. Now we're going to triple mass 2. So mass 2 is going to go up by 3. That means force is going to do the same thing. So up by 3, so 200 times 3. And that gives you 600 newtons there. Okay, now we're done with that part. Now double the distance. Okay, so distance, so we're going to keep that d squared there so we don't forget it. So distance is going to double. Okay, so the opposite of doubling would be to divide by 2. Okay, but remember distance is squared in this case, so you're going to do the opposite squared. So divide by 2 squared, which would be divide by 4. Okay, so you're going to take that 600 divided by 4, and you're going to get 150 newtons. Okay, and that's your answer there. Now we're going to do another example. So just in case that was a little confusing, we're going to do another one. Okay, so now what we're going to do is we have our same 100 Newton force. I'm going to double both masses and cut the distance to 1/3 of the original value. Okay, so I'm going to do this a step at a time. So mass 1 is going to go up by 2. So my force has to go up by 2. So 100 times 2 gives me 200 newtons. Okay, now I'm going to double mass 2. So if mass goes up, force has to go up. So that's going to double again. So 200 times 2 gives me 400 newtons. Now, could you have done this all in one step and just quadrupled it? Yeah. Okay, but if that ever gets in the way or that gets confusing, just take it a step at a time, and that'll just make it a little more simple. Okay, now what we're going to do is we're going to cut our distance to a third. Okay, so distance squared, so we're going to leave that squared there, is going to go down by, it's going to divide by 3. Okay, so that means if distance goes up, force has to do the opposite. So I'm sorry, if distance goes down, force has to do the opposite. Force is going to go up. Now, the opposite would be multiply by 3. But that squared's there, so multiply by 3 squared. So that's technically the same thing as saying multiply by 9. So 400 times 9 is going to give me 3,600 newtons. And that'll end that one.